So today we're going to be talking about simultaneous equation models, and we will define, and describe what are simultaneous equation models. We will provide an example. Then we'll talk about the structure and reduced form models related to simultaneous equation models, which are different ways in which we can write simultaneous equation models. And then, once we understand the structural and reduced form models, we will talk about what's called the problem of identification. So, it's likely, so today, this is, kind of like the first part, kind of like the just theory part, like an introduction to simultaneous equation models, and several issues that we need to discuss before we talk about estimation of the models. Okay, so to describe these, simultaneous equation models, which I will be calling SEM, let's go back to what we know regarding systems of equations. The previous models that we talked about are the seemingly unrelated regression models. If you remember, in the seemingly unrelated regression models, which we wrote it this way, so we have yi equal to xi beta I plus ei. So each of these equations represent one of the equations in the system of equations. So we talk about m equations, and the issue there, and it's called seemingly unrelated regression models because the equations are related through the disturbances. That was kind of the key idea behind these models. The equations are related through the disturbances and sometimes, so you see in the context of demand systems, we also say that they are related through some of the parameters. But mainly, the main idea has to do with the relationship through the disturbances, because in the difference equations, remember, we have observations that correspond to the same individual. That's kind of like the main idea. In simultaneous equation models, on the other hand, okay, we also are going to have this relationship, from in the different equations through the disturbances. But in addition to that, we're going to see that the equations are related through the model variables, and more specifically, the dependent variables. So in simultaneous equation models, what's going to happen is that the dependent variable in one equation is also going to be the explanatory variable in another equation, and so on and so forth. So simultaneous, again, equation models, and that's kind of what the simultaneity comes, and that's what they take the name, because, again, some of the dependent variables in one equation can be explanatory variables in another equation within the system of equations. Okay, so let me write that down. So in simultaneous equation models, the equations are related I'm writing too fast. Are related through the disturbances and also the model dependent variables. That is the yi's. And the idea here is that the dependent variable in one equation is the explanatory variable in another equation. The dependent variable in one equation is the explanatory variable in another equation. Another equation. So that's kind of okay. So I'm gonna give you this example. So let's look at an example. So let's say that we have an equation, a system of equations with two equations. So the first one, we're gonna have beta 1 0 plus beta 1 1 y2 plus beta 1 2 x1 plus an error term. In the second equation that we're considering, we have 2 1 y1 plus beta 2 2 x1 plus beta 2 3 x3 plus error term. So as you can see here, see y2, which is the dependent variable in the second equation, is explanatory variable in the first equation, and y1, which is the dependent variable in the first equation, is also an explanatory variable in the second equation. Okay, so this is an example of a simultaneous equation model. And of course, you know, the same as in the similarly unrelated regression, the errors are also going to be correlated because we're going to have observations for the same individual in both equations. So we're also going to have that type of correlation. Now, to see how this, you know, this problem of simultaneity works, let's look at the classical example. The classical example of simultaneous equation models is the market equilibrium model from economics. Okay, so in the market equilibrium model, basically what we're trying to analyze is the demand and supply equation. So this is the demand equation and this is the supply equation. Okay, so the demand equation, the way that we write it, we write the demand equation. We can say that Q, which is the quantity demanded, see, is a linear function of the price, and also, you know, it depends on some other factors. Oops. Like here we're gonna use income. So this is the price, and we're gonna call this is the error for the demand equation. And we also have a supply equation. Q, so I'm gonna call it QS, it's gonna be equal to, and here I will use betas. And so in each equation, what I'm doing is I'm gonna having an additional factor in addition to the one that, you know, we have in the graph. We're considering another factor that affects supply. So this is what's called sometimes, you know, a supply shifter. Okay, so in the demand equation, what we see is how the price affects the quantity demanded, and, you know, of course, the quantity demanded can be also affected by other factors. Here we have income, and the supply equation, which, well, the demand equation defines the quantity of a good that is demanded at different levels of prices, and the supply equation is the quantity that's supplied by producers at different levels of prices. So so here we have the supply equation. So the higher the price, the idea here is that the higher the price, the larger the amount that producers are willing to produce. On the other hand, in the demand equation, is the larger the price, the lower the quantity that consumers are willing to demand. So that's kind of the relationships that we have defined here. So this is the demand relationship, and this is the supply relationship. Okay, so in this model, in an equilibrium, we know that the quantity demanded is equal to the quantity that is supplied, and therefore in this model, the model determines jointly both the quantity and the price. Okay, so and they are both variables that are endogenous. Both variables are endogenous in both equations. So this model, let me see. Sometimes the thing jumps too fast. Apologize for that. So we were here. So here in equilibrium, the quantity demanded is equal to the quantity supplied, and this model determines jointly quantity and price. These both variables well, let's say both endogenous variables are in both equations. Okay, so in terms of the definition, you can think that Q is y1 and P is y2. Now I know that you at this point you might be wondering, well, when you gave us example, we had y1 as the dependent variable one equation, and y2 as the explanatory variable another equation, and y2 as the dependent variable one equation, and y1 as the explanatory variable another equation. But in this demand and supply equation framework, basically we have y2 as the dependent variable in both equations. And that might look a little bit confusing, but the reality is actually, we can rewrite any of the equations as a function of the price instead of having it as a function of quantity. So if we were to rewrite it, either the demand equation or the supply equation, where we have price as a function of quantity demanded, we will have a model like the example that I showed you previously. However, notice that, and there is an error here. Sorry, here I'm going to have to apologize. So this is the equilibrium. That was an error. So this is Q, the equilibrium price, and this is the equilibrium price and the equilibrium, the quantity. And here what I wanted to say is that the quantity demanded is equal to the equilibrium price, which is equal to the quantity supplied. And we write the demand and the supply equations in terms of the quantity, because we can make use of this equality to be able to solve for price or the quantity demanded. And I'll get to that in a minute. Okay, so again, this is the typical example, and again, even though it's the typical example, the way that we write it is not exactly like the textbook definition of the simultaneous equation model. But again, we can rewrite any of the equations, price as a function of quantity, and then we'll have the model written in the way that we had written previously. Okay, so the idea here is, again, so we have these two equations. The idea is, okay, we cannot use OLS because we have an endogenous variable, on each equation as the explanatory variable. And let me see, and I'm going to show you right now why is that we have endogeneity. So in this system, basically the idea here is that we can't use OLS because we have an endogenous variable on each equation. An endogenous variable on each equation. Okay, so let me see, to show endogeneity, again, we can make use of the equality of the quantity demanded and quantity supply, and then we can solve for P. Solve for P in the system. Okay, so again, so we said that the quantity in equilibrium, the quantity demanded is equal to the quantity supply. So basically we can have both equations plus alpha 3e plus ed is equal to beta 1 plus beta 2p plus beta 3s plus the error in the supply. So if we solve for p here, it can be shown that it's going to be equal to beta 1 minus alpha 1 minus alpha 3 income plus beta 3s plus the error in the supply equation minus the error in the demand equation divided by alpha 2 minus b2. Now, so this is the formula for P. Now, the thing here to notice is, and sorry, I lost that one. I didn't mean to do that. Is that price depends on both error terms. So the price is correlated by the error terms. And remember, that's by definition, that's the definition of endogeneity. If we were to run OLS in any of the equations separately, since the price is a function of the error term in the supply and the demand equation, that means that we will have endogeneity, and therefore we cannot use OLS. Okay, so since P is a function of the error terms for both the demand and the supply equation, it is correlated with them. So the use of OLS to estimate QS and QD will result in biased and inconsistent parameter estimates due to endogeneity. The use of OLS to estimate QS and QD will result in bias and inconsistent parameter estimates. Due to endogeneity. And that's what's called the simultaneous equation bias. Okay, so that's kind of what's going on, and that's where that simultaneity problem comes into place. So in this system, and some terminology here. So in the system, Q and P are called endogenous, or jointly determined. On the other hand, I and S are exogenous. Exogenous. Let me write that well. Okay, so hopefully this example, although again, it's kind of sometimes hard to follow given that the way that we write this is the classical example of simultaneous equation models in the context of economics. But it allows you to see, I mean, what's going on. And again, the idea here is that we have these dependent variables which are a function, which become some dependent variables in one equation become the explanatory variables in another equations. And with this example, we can see how this, the problem of simultaneity. Now, when we're talking about simultaneous equation models, we have what's called the structural form and the reduced form models. And the structural form is the way that we write the equations, in its original form. It is taking a little bit to save. These coefficients, so hopefully it saves fast. Give me a second. Wow, taking quite some time. Okay, so this is, there are two ways to write the simultaneous equation models. One is the structural, and the structural is the way that we write the equations originally. And, and to explain these concepts, I'm using the example of our demand and supply equations. So our demand and supply equations, in the way that we write it normally, that's what's called the original form, or kind of like the structural form. And we can go from this structural form to what are called reduced form models. And in order for us to do that, we rewrite our equations. So basically, you see here what I did is I moved all of the variables to the left, but the error terms. See, here we have the error terms, and everything else for both the demand and supply equation, I move it to the left. Notice also the way that these equations are organized, because we have the endogenous variables to the left and the exogenous variables to the right. And when you are studying, it would be good if you can try to replicate this, the procedure. And then we can write this system in after we have rewritten this way, we can rewrite the system in using matrices. So this system of two equations using matrices can be written in this way. So we have Qi Pi, and then so all the coefficients now are a matrix. And here we also have including the intercepts. And I don't know why this thing is not saving. It's giving me some. So let me see. It's not allowing me to delete things. I think I'm in trouble. I don't know why. I'm trying to clean up things. Well, let me see if I can write. Well, at least I can write. Even though I cannot correct things. Oh, wow. Sorry, I don't know what happened. Oh, well, it's not working. So, basically what I'm doing is I'm rewriting the system of equations using matrix form. Now, something to notice here is the system here. What I have is the way these matrices are written is a little bit funny because I have 1 by 2 times 2 by 2. So this is the vector of coefficients. And I encourage you to try to see if, using these matrices, you can go back. The idea here, try to go back to these two equations, and you will see that works. So basically what I'm doing is instead of writing the equations, this is in regular form, I'm trying to write using matrix forms. And what I'm doing is I'm separating the variables, the endogenous variables, and the exogenous variables from the coefficients. Okay, so that's kind of what I'm doing here. So try to replicate what I did here, but it's just a way to rewrite it. So I end up with, again, so I'm going to have this vector of coefficients, which I call it yi tilde hat. Okay, so let me see if I can write it here. So here, let me see. So this is what I'm going to call later on yi hat prime. This matrix here is what I think that's sigma. This vector here is what I later on call xi tilde. And this matrix of vectors is what I call B. And this is what underneath I call E tilde I prime. Okay? So that's what I have there. I've just rewrite it. So, and this is what's called the structural model, in matrix form. Okay, kind of the original equation, but kind of, rewritten. So this is what's called the structural model. Okay, so basically it uses the equations in kind of its original form. Now, to get to what's called the reduced form model, we need to solve for yi only. So remember, yi, what we have is the vector of only endogenous variables. So what we do here is, we solve for yi, so yi hat, and again, I'm using this equation is going to be equal to minus xi tilde b times this omega inverse plus the error term times omega inverse. And then what I do is this product. So remembering what we have here, these are matrices of coefficients. Okay, so I'm going to call that pi is equal to beta times omega inverse. And here I'm going to create like a new error term. I'm going to call it a bi tilde hat, which is going to be the product of the original errors times omega. And if I do that, I end up with what's called the reduced form model. And basically what we have in this reduced form model, what we have is the endogenous variables to the left and all the exogenous variables to the right. So intuitively here again, what I try to do is I try to have only endogenous variables to the right and all the exogenous variables to the right. And now that might look a little bit complicated, but basically, and in the past I used to spend a lot of time doing this. Here I only want you to get the intuition of what's going on. So basically, for our example, if we were to write the reduced form models, we will end up with Qi equal to pi 1 1 plus 2 1 I pi 3 1 Si plus beta I 1 and Pi equal to I plus, so this is that matrix here. Oh, remember, this matrix here of coefficients. Okay, and this is what's called the reduced form model. Okay, so in the reduced form model, so this is the thing for you to remember. In the reduced form model, each endogenous variable is a function of the exogenous variables only. Okay, so that's the key things to remember. Sometimes in exams, and here, this is not like a total formal proof, because I have jumped a lot of steps. Basically, I'm just giving you a sense of how do you go from this structural to the reduced form model. I mean, you can do mathematically. The reality is that most of the time, I mean, we don't do that anymore in econometrics. So the thing to remember is that, you see in structural models, we have, in each equation, we have both endogenous and exogenous variables. Okay, so that's kind of what we have in a structural model. You see here in our demand equation, we have Qi and Pi. In the supply equation, we have Qi and Pi. Okay, so that's what we have in the structural models. If we go to the reduced form models, you see now in the reduced form models, we have Qi only as a function of both exogenous variables, and we have Pi only as a function of the exogenous variables. We can do these derivations mathematically, and actually, I mean, if you see here, so note that each of these coefficients is related to the original coefficients. Actually, it can be shown that each pi coefficient, is related to the what we call the b and the omega inverse coefficients. Remember, in the omega inverse coefficients, we have the ones and the alphas, and the betas, we have alpha, beta. So there are kind of complicated functions of that. And actually, you could show that. But nowadays, I mean, in econometrics, we really, in the past, I mean, we used to spend a lot of time doing that, going back and forth between the structural and reduced form model coefficients. But in reality, nowadays, we don't do that anymore. So what I wanted to show here, and I know that it looks a little bit complicated, is that in the structural models, again, in each equation, we have both endogenous and exogenous variables. But in the reduced form model, we have as dependent variable the endogenous variables, and as explanatory variables only exogenous variables. Okay, so, and the other things to remember is that each reduced form coefficient is a function of structural coefficients. the structural coefficients. Okay, so again, if we were to write that matrix here, matrix pi, which would include all of the coefficients, all the pi's, pi 1, 1, pi 2, 1, pi 3, 1, pi 1, 2, pi 2, 2, and pi 3, 2. All of them, this could be a function of the original coefficients. Okay, so that's kind of it. So this idea is clear. And again, here I don't show you a formal proof on how they are related. Nowadays, that's not really necessary. If you are really interested, I think that you can follow in green and read a little bit more this example. But again, nowadays, most of the time we don't do this type of derivations. Which take us to the third thing that I want to talk about today, which is the problem of identification. So once we understand what are those reduced form and structural forms, we can talk about the problem of identification. So and basically the question here with the problem of identification is the following. Is it possible to recover the structural model coefficients from the reduced form models? Okay, so in the past, that's a question that used to be asked, because a lot of times you will go and you will estimate these reduced form models and then use those to recover back the structural model coefficients. But nowadays, the same question can be worded in a different way or look at from a different perspective. Nowadays, the emphasis is in the question if it makes sense to estimate the model that we are proposing. So does it make sense to estimate the model we are proposing? Okay, so for example, let's say that you have a project and you decide that the model that you should consider is the following. So this should be y1. So we have y1 as a function of y2. Let's say x1, x2, and we have an error term. And we also have this model alpha 1 x1 plus alpha 2 x2 and this error term. So the question is, so does it make sense to estimate this model? Can we recover all of the coefficients of this model? So let's say that, after your theory, so again, here the question is, can we estimate all the equations? Can we estimate all the coefficients of both equations? Okay, and the answer is going to be no. Okay, and this is the problem of identification. So the answer is no. Okay, only the second equation can be estimated. The first equation we're not going to be able to estimate. Only the first equation can be estimated. Okay, now, and then some of you will be saying, okay, so, but I mean, why did you spend all that time, talking about the structural and the reduced form model? Well, the issue is that, like for this model that I just wrote, of course, we could write, so this is, we could write it like the structural equation in matrix form, and then, try to see the reduced form model and see if we can go back from the reduced form model to the structural model, and the answer would be no. Okay, if we were to do all that mathematical analysis, the answer is going to be no. We will not be able to recover the beta and the sigma coefficients from those pi coefficients. Okay, so that's kind of the relationship. Because remember, we estimate these reduced form models, but most of the time we're not interested in the reduced form models. What we're interested is in the structural coefficients. I mean, we're interested in those coefficients related to the supply and the demand equation. We're not interested in the reduced form models. So we could do the math to see if we can go back from, from the pi coefficients to the b and the omega coefficients. Okay? So we could do it mathematically, but it's an easier way to go about doing it. Okay, so how do we know if the system is identified? If the system is identified, or another way, if we can estimate all of the coefficients in that system. Well, so one way to go to do it is using math. Using all those systems of equations. And you see that's kind of even problematic for the case where we only have two equations. When we have three equations, things become kind of, crazy. So this is not practical. Okay, so the second way to do it is just checking formal mathematical conditions. Formal mathematical conditions. Okay, and there are two mathematical conditions. There are two conditions. So the first one, and I'm going to call it 2.1. So the first one, it's what's called the rank condition, which in practice, in economics, which is not checked in practice, to be honest with you. In practice. And it is related to restrictions in the coefficients. And it's not checked in practice because most of the time, for the type of models that we write, it is satisfied. So for example, the right condition, what we're talking about is if you see this model, for example, that we were proposing here, in a way, you see, in a way, we're assuming that the coefficient for y2 is 1, okay? So if we were to write a model, when we write here like a coefficient, something like gamma 1, y2, I mean, then probably that rank condition will not be satisfied. But again, most of the time it will run a model that kind of makes sense. Or, you could kind of, again, attach a coefficient next to the error term and trying to estimate that type of model. Or, I mean, if you were trying to estimate a model where we have alpha 2 divided by alpha 3 and try to estimate that model, that probably won't be, the rank condition won't be satisfied. So, if you overall you write models that make sense, that rank condition is going to be satisfied. Okay, so related to restrictions of the coefficients. So, for example, here we're assuming that the coefficient for the dependent variable is always 1. For the yi's is 1. Okay? So if it was not 1 and we were trying to estimate another coefficient, there probably will get in trouble. So the most substantive or the most important condition that needs to be checked is what's called the order condition. Okay, so and what does that order condition tell us? Actually, very straightforward. Basically, the order condition tells us that the number of exogenous variables elsewhere, this is in other equations, only, and I add this only in a second. I'll tell you what I add this on. That only number of exogenous variables elsewhere in other equation in the system of equations is higher or equal to the number of endogenous variables that we have as explanatory variables in each equation. As explanatory variables in each equation. In each equation. Okay, so this condition actually needs to be checked equation by equation. And I think that this rule, when you see it in the context of an example, makes more sense. Needs to be checked equation by equation. Okay, so let me give you a couple of examples. And let me see if this works. So let me see example 1. So that's the system that we already talked about before. Pi plus alpha 2 I is ei1, and the other equation was beta naught plus beta 1 pi plus beta 2 s2i plus e2i. Well, ei2. Okay, so let's see if the other condition is satisfied. So how many endogenous variables we have in the first equation? We have one endogenous variable as explanatory variable. Explanatory variable, and that's pi. So how many exogenous variables in other equations we have? We have one exogenous variable in other equations. And that is Si. Okay? Therefore, the other condition is satisfied for equation 1. Okay, again, let's go back. Number of exogenous variables elsewhere, and that means in other equations only, in the system of equations has to be higher or equal to the number of endogenous variables that we have as explanatory variables in each equation. Again, in the first equation, pi is endogenous variable that we have as explanatory variable, and in other equations, we have si as exogenous variable in the other equation. So let's look what happens in the second one. Again, we have one endogenous variable as explanatory variable, as pi. And if we look at the other equation, at the first equation, we only have one exogenous variable in other equations. Okay, so and that should be II. And therefore the other condition is satisfied for equation 2. So if it's satisfied for both equations, then that means that the other condition is satisfied for the system. For the system. Okay, so let me give you another example. Very fast. So now let's say that the system that we're considering, we don't have another explanatory variable here for our demand equation. Beta 2 is I, that's AI2. Okay, so here again we have pi, which is, we know that's endogenous. Okay, but we have in another equations, we have Si as exogenous in another equation, so the other condition satisfied for equation 1. In the second equation, we have pi as endogenous, but elsewhere in the system we don't have any exogenous variable. So the other condition is not satisfied for equation 2. And therefore the other condition is not satisfied for the system. Not satisfied for the system. Okay? So I'm going to give you an example 3, but I'm going to let you think about it. Then maybe we can discuss it. Okay, so I'm going to give you this system, and then you have to think if the other conditions are satisfied. So think about the system. Plus beta 2x1 plus beta 3x2 plus beta 4x3 plus E2. Okay, so this is a little bit more complicated, but I want you to be thinking about it. And then, we'll be discussing this example, okay? So to summarize, today we've talked about this, simultaneous equation models. These are equations that are related not only through the disturbances, but also through some of the dependent variables. So some variables that are the dependent variable in one equation are explanatory variable in another equation. We talk about the traditional example of supply and demand equations, aggregate supply and demand equations, and I show you why we have this endogeneity problem. We also talk about the structural and reduced form models, and that led us to the problem of identification, and which kind of give us a practical rules to see if we can identify or not all the coefficients in a given equation. So we need to do the check equation by equation. If all the equations pass this other condition, that means that the system, all the coefficients in the system can be estimated.